Okay, it's 8:40. Let me start my presentation. Thank you everyone for coming today. The topic of my presentation is Liu-text code-line and objective vortex identification method. The motivation of this work is like the first time when when Dr. Liu proposed Liu-text and we introduced this concept to other scholars. And one response we got from others is that the vortex structure shown by Liu-text is quite similar to other already existed method. Because at that time we only use isosurface, Liu-text isosurface to show the vortex structure, and of course they look similar. So that motivates us to make use of the distinct feature of Liu-text. Liu-text is a vector, so we would like to make use of that feature to develop some special way to visualize the vortex. Then we develop the Liu-text code-line. So on the screen I show you a figure of Liu-text isosurface, and what is the limitation of an isosurface? Well, from an isosurface, usually it's difficult to show strong and weak vortices simultaneously. So I think you are familiar with the turbulence transition, right? So for the turbulence transition, the first stage, there do have some span-wise vortex, right? That's the Toming slitting waves. But if you pick a threshold, these part of the vortices cannot show because they are too weak. But if you pick a too weak threshold, you can see these structures, but the later part will become not clear. And also the second limitation, the isosurface is influenced by the choice of threshold. Yes, so the choice of threshold is we do not have a uniform standard which threshold is good, which threshold is bad. We just adjust and view the structure by our eyes. So not very rigorous. And third limitation is looking at the isosurface, we cannot tell the direction of the rotation. Maybe you may say, like, for these lambda vortices, you can tell the rotation direction because the shape of the isosurface is like a line. But when the vortex structure becomes more complicated, more like it's not show you a clear direction. So we do not know how the vortex is rotated inside the isosurface. And the last limitation is the vortex structure isosurface does not tell you how the vortex strength change. Maybe you can tell the vortex strength for this simple vortex because you may say at here the vortex strength is stronger because it's thicker, right? Because it's thicker. But like for the later stage, if look at the ring, so the ring is vortex strength is stronger at the ring or at the neck, or that's what we cannot know from the isosurface. And I directly give you a comparison between the vortex code-lines and the isosurface. So the isosurface you've seen, right, and The top is the pure vortex co-line, and the last one is isosurface plus the co-line. So like we can see the front structure, right? The weak vortex structures, and the color on the lines represent the Liotex stress. So we also can know the rotation stress of the vortex. For example, if we look at the lambda vortices, you can see here, right? It's the stronger, the strength is stronger. And if we look at the ring, you can see the red region is at the neck, not the middle of the ring. So we know at the neck, the vortex is stronger. And also we can know the direction. So it's a line, then its tangent direction is the local rotation axis. Yeah. So look at this figure. Which way you would like to visualize the isosurface vortex structure? I bet most people would say you will like the co-lines, right? The co-lines show you more structures and easily help you have a better understandings of the vortex. And yeah, this is a limitation of, this is the problem caused by the choice of threshold. I think Dr. Liu also mentioned yesterday. So if you choose a large threshold, the vortex look like breakdown. If we choose a small threshold, the vortex looks like continuous. So that is a man-made issue. That's an artificial issue. So we would like to try to avoid it in the research. Okay, then the definition. So we introduce to you how do we implement. What's the definition of Liotex co-line, and how do we implement to find these co-lines? So the definition of Liotex co-line is the Liotex co-lines are formed by the points that located at the position that satisfy this condition. So we require the gradient of R cross product, the direction of Liotex, the literalize the direction of Liotex being 0. And of course, that position should have rotation stress. This condition essentially means we would like the gradient line to be parallel to the local Liotex direction, right? Parallel. The idea is we would like to find some the point that is the local maximum. So at a point we can find Liotex direction, right? And perpendicular to that direction there is a plane. Then we find the largest Liotex point in that plane. Maybe you can see, understand it clear from this example. So this is the streamlines of Berger's vortex, and the red line is the detected Liotex co-line. You can see it is the vortex co, and so this figure explains the idea. So we have a Liotex direction, and there is a plane perpendicular to this direction, and the point that's the local maximum inside the plane is the vortex center point, right? So you can see these black lines are the gradient lines. So the gradient lines, you can see the gradient lines is perpendicular. It's normal to the text direction unless it reaches the maximum, right? So like as I said before, the cross products being zero essentially means they parallel, right? So like for majority positions, they are normal, so they only be parallel at the vertex center. So that's why we give the definition of mutex like that. Also, you can see this figure. So these black lines are the mutex gradient lines. Mutex gradient lines starting from these points, right? This point. So you can see apart from the vertex center, the gradient line is vertical. It's almost vertical to the mutex co-lines, but at the center they become parallel, right? Become parallel. The definition is very clear, and it was first proposed in 2019, but it has been a long time that we haven't found out a good algorithm to automatically find the mutex co-lines. So what are the challenges on directly implement the definition? Well, also look at this figure. So the challenge is the parallel behavior only exists in a very close to the vertex center. You can detect parallel. Otherwise, you only can see the normal, is perpendicular. And this is the figure of the relation about the distance to the mutex core and the angle between the mutex direction and the mutex gradient. Of course, the vertex core, we want it to be zero, right? Yes, the angle be zero, that's parallel. And you can see if the distance is 0.1, the degree of their angle is around 80 degrees. It's still huge, large degree. It's like normal, right? So the data on the left figure is from this line. Okay, it's from the red line. It goes to the mutex center, and like when we directly apply the definition, so we numerically we may give a threshold. If the angle is less than 5 degrees, for example, we consider they are parallel. But if you require 5 degrees, it's super close to the vertex core, and you can see the grid point and the vertex core line position. So this is the grid point of our simulation of DNS, right? DNS, is using a lot of points, already using a lot of points. But even for the DNS level grid points, there are also some big gaps. So when we try to directly implement the definition, we find for one vertex structures, we may just find 1 point, right? If we tolerate 5 degree error, but maybe we can only find this point because it's very close to the vertex core line, but we will miss this one and this, right? But if we give big error tolerance, you will find a bunch of points, too many points. So that is the challenge, right? That is challenging. So that's why after 4 or 5 years, we did not find an ideal method. And based on our definition, So at the vertex center, the gradient line and the mutex line should be the same, right? Because we require them to be parallel. If they are parallel everywhere and they pass the same point, the two lines should be the same line. But when we play with our DNS results, what we found is they are not necessary to be the same line. So like for the strong vertex, they can be the same line for a period, right? For a period. But like for weak vertices, it can be a big discrepancy. So the color line, the colorful lines are the gradient lines, and the color represent the mutex strength. So at the blue, right, the mutex strength is quite weak, and we draw the gradient line and the mutex line from the same point. You can see big difference. So that's another way. So at the beginning, we use mutex lines to draw the vertex structure, because after finding a seed point, you can draw the whole vertex structure. But that may arouse error, especially for the weak vertices. To develop a good way to find mutex core lines, which line should we use? We use gradient line, or do we use mutex line? Both lines has their advantages and disadvantages. For the mutex lines, the good thing is we can easily find the entire vertex structure. So selecting a seed point, you can draw a long line. But the drawback is it's because of numerical error. It's hard to find a good one, because even though the seed points you pick are all at the vertex center, but the lines will not overlap. You can see from the example. So I choose these 3 red points as the seed point, but you can see the mutex lines can be 3 different lines. Like you see, can be 3 different lines. So that means for one vertex, right, you need to avoid this duplicated or more lines, you need select a unique, right, seed point. So that may be doable for easy vertex structure, right? But when the vertex become turbulence, it's a chaosis, and it's maybe not very know how to do that. And for the gradient line, so the good thing is you don't need to worry about like duplicate lines, so more lines, because gradient has a intrinsic feature to converge to its maximum. Right? We know gradient always point to the maximum, so it can tolerate some error for the beginning point. Right? So, for example, if we look at this figure, so the gradient line start from the very not at the vertex core. It departs. It's apart a lot, but finally it will converge to the vertex core. Right? That is a good thing of gradient lines. It can converge to the vertex center. So you do not need to worry about the choice of your start point. But its drawback is the gradient line stops at the maximum, right? When the gradient line really reaches the 3D maximum, it stops. So for example, we start at here, the gradient line goes, and it stops here. Then you will not get the vortex core line for the rest. If you like draw another gradient line from here, it will converge to goes to this maximum. So this is the problem of the gradient line. You cannot hard to get a entire or complete structure of the vortex structure. So this figure. So each line has its strong and weak property. So what do we do? So the solution is to combine these two lines together. So we use the method, the predict and the correct method. This method was first proposed by Banks and Singer, and in their original paper, they use vorticity and pressure, and now we replace vorticity and pressure to Liouvtex and the Liouvtex magnitude. So let's look at the figure. So these figures are from Banks' paper. So what do they do is, okay, so we have a point on the center, and we find its next point, find pi plus 1 by the they use vorticity direction, but we use Liouvtex direction. Okay, Liouvtex direction. So we find its next point, and at the next point, they create a plane perpendicular to the vorticity direction at the next point. But we create a plane perpendicular to Liouvtex direction at that point. And after that, they find the minimum pressure, but we find the maximum Liouvtex. So how does this predict and correction method combine the advantages of two types of lines? So we look at the first step. So the first step is actually doing the thing of Liouvtex line, right? So we find a point and we go along the direction of Liouvtex, find the next point. That's the process to draw Liouvtex line, right? So we use Liouvtex line in this step. And we also use the gradient line. So we find the Liouvtex maximum in the plane. So that's make use of the gradient feature, right? The gradient converge to the maximum. So this method overcomes the drawback of a gradient line. So here, right? So here stops, right? Stops. If we draw gradient line stop, but this point does have Liouvtex direction. So we can still find the next point along the Liouvtex direction. And that may have some error. Then correct it by the Liouvtex gradient, right? So then we can easily get a long, continuous, good Liouvtex core lines. So let's see the sorry. No. Okay, yeah. Sorry. So that's what we do to use both advantages of these two types of lines. Then this is the general idea to find the Liouvtex core line. So we first find the points at the vortex center. So we first just find points. We scan the domain and find points. And then we group these points into lines. Then we remove some noise points. So let's look at how to find points at vortex center. So we still go back to the definition of Liouvtex. So the definition requires parallel. So a straightforward method is we just check the angle, right? Check the angle between these two directions. If the angle is 0, they are parallel. But as I have mentioned before, this condition requires the point very close to the vertex core. So its efficiency is low, right? So if and it may miss some point. Yes. Then the second way is we know that it's the local maximum, right? Local maximum means it's the point is greater than or equal to its surrounding points. So we just do not calculate the angle between these two directions. We just check if the point is bigger than its surrounding points, right? That can increase the efficiency. Let me explain the idea. So if we have a point, right, we want to determine if x0 is located as the vertex center. And we first find its lutex direction, and then we find four points in the plane perpendicular to the lutex direction. If, this is the figure in that plane. If the middle point is greater than or equal to both 4 points, then we think this point is the vertex center. It's located as the vertex center. And by doing this, we increase the detection distance, right, to the half d, right? So if this distance is d, and this figure shows the extreme situation that this method can detect x0 is located on the vertex center. So if we have 2 points, but the real vertex center is located in the middle, as I showed you before, if you check the angle, this point must be very close to the real vertex center, then you can notice, you can say this point is at the angle. But if you give a d, then as long as the distance between x0 and the vertex center is less than d over 2, then you can say x0 is near, at least near the vertex center. Right. So when we actually run the program, we combine these two methods together. So we first use the method 2 to quickly check if that point is at least near the vertex center. So if it's near the vertex center but still has some error, then we use the then we go along the gradient direction to correct it more close to the real vertex center. You can see the effect in these 2 figures. So the above figure is the result we get simply purely applying the second method, right? We compare the points with its surrounding points, right? And since we increase the efficiency, but we lose the accuracy. So you can see it's like separate, because that's the d, right? That's the d. So it's like separate straight lines. And then after finding this point, we let these points go along its gradient direction, right? Then and achieve the good effect. So these points are not just grid point. So as I said before, the grid point may be not enough. So I use more points. I interpolate the value at that more points. So not just use the grid points. And these so although you look at it as a line, they are points. Okay, they are points. So these are the points. And then we go to the group point session. So then we group this point into lines. This is what we do to group points. So the idea is simple. So we start from any point, right? And for the unused point, if we use points, we just don't consider it later. So we just, for example, we randomly select one point, for example, this point, and of course we have a threshold. So we find if its closest point is within our given threshold, right? Because the next point cannot be too far away, right? So because I use more than a grid point, so I would assume the distance between the previous point and the next point should be close. So we need to check if they are close, and if they are close, then we check the direction of the direction of the x matching is actually the gradient direction. So the gradient direction is the gradient direction is the real vertex code direction. But since we do numerically, we can tolerate some error. So if the angle is almost parallel, but less than a threshold means we want them to be parallel, but we can tolerate some error. And if these two conditions satisfied, then this point is the next point. And if this condition not satisfied, we find the second next point. Well, because it's possible that its closest point is at here, right? So not along the gradient direction. Maybe its closest point is this point. It's opposite direction, but this point do have its next point. So we need to check the second closest point, and until all the points within this threshold has been checked, right? Okay, and knowing how to determine the next point on the same line, we group them. So we first check if the point set is empty or not, and the n represents how many points in the line we find, and m represents how many lines. So just like we start from a point, then find its next line, right? We find if this point has next line, we find it and continue, right? Find the next point of the next point. So we just keep doing this process until we find the last point, right? So until there is not a next point, okay, then we get a set of lines in the on the same line, and then this point forms the first line. And if we still have unused points, we continue doing this process. So we just, okay, so the number of lines plus 1, then we keep doing from the first point, find next point, from next point, from another next point, until we cannot find the next point. And there may be a possibility that the second point linked to the first point, right? Because the gradient has direction. It's possible that the second point linked to the first point, second line linked to the first line. Then we combine these two lines together as a one line. So that's just this process, and keep doing until all points has been classified in one line. Then we finish the group process. Yeah. And this figure shows you the result. So suppose we want to group these points, right? So at the beginning we don't know which points belongs are on the same line, but after we run the mentioned program, and the color means these points are recognized on the same line, right? So you can see we correctly distinguish the points on the same line, right? Okay, and then after that we just remove the noise points, because it's possible that maybe after grouping lines, one line only have 3 points, like one line only have 4 points. That may be a too short vertex structure, or maybe it's a noise. So if you don't want, to make a clean result, so I just delete these lines, right? The lines that only contains a few points, right? Where I throw them away. But if you want to study them, you can keep them. It depends on your need. So let's see some results. So still the result, this is a flat plate flow. So it's a turbulent transition. The early edge is a TS wave, right? You can see by applying the Lewis-Colline method, we clearly see the structures of the TS wave, and also for the late stage, right? So we we can also we can capture the weaker vertices. We can show them simultaneously, and I need to classify. So in this figure, I filtered out some too weak vortex regions. So I first filter this region by omega. So I first filter this region by omega. If the region where omega is less than 0.5, I just don't consider them. So you will see actually here you can find more detailed vortex structures here, but I do not show them in this figure. And this figure gives you a top view of that result. So the structures are very clear, and you can see where the rotation is stronger, where the rotation is weaker. Yes?
There's a question online. It says, it seems that rigid rotation will not be captured, and almost rigid rotation might be challenging. Is there a workaround?
Rigid rotation will not be captured. That's, I can.
And then what are the initial lines at 325? Are they accurate? I think
325, are they what?
Are they accurate?
Accurate.
The initial lines on 325.
Yes. You mean here?
I think on the previous slide.
Here?
Yes.
Are they what?
Accurate.
Accurate. You can. I think they are accurate because I checked by. So what do I check? I find these lines, and I also draw gradient lines, and you will find the gradient lines converge to the lines I captured. So I believe they should be accurate. Of course, they can have numerical error, but the gradient line converge to them. Yeah, I checked the result. Yes, and like, so you can also observe some structure we do not know, right? So So you can see these, right? So at the first time I saw these, I also think they are noise, and I tried many methods to remove them. But if you see the whole process of the evolution, you will see this part is not noise, and it has the you can see. Yeah, I will show you the movie of its evolution later. So and this is a side view. So you can see at the front it's almost a dot, right? The span-wise, what is it? Almost a dot, and then this the line. It has this increasing angle, right? It's going up, and also the vortex ring roll up, right? Vortex ring maybe here roll up. It's almost vertical, and so very clear vortex structure. And then we take a close look at the region A. We can take a look at an enlarged view of the region A. Well, region A is some kind of complicated, right? Not a simple vortex structure. And you can see these, maybe you feel like they are in a mess. And I then remove the weak vortices. I only keep the vortex co-lines inside the isosurface. Then you can see these vortex co-lines matches the isosurface pretty well. And if you draw the gradient lines, they converge to these the colorful lines. So this method work for complicated vortex structures. And then we can look at the region B, right? The region B. So you can observe some weird, right, vortex structure here. Looking at the color, they are blue, so they are very, very weak, right? They are very, very weak compared with its surrounding vortex co-lines. Like you may question whether this structure really exists. Are they correct? Then we just reduce the threshold of the isosurface. Right? You can see they do have a vortex here, right? Because I reduced the threshold to a small threshold, and you can see these lines are really included in the vortex isosurface. And also, let's look at the region C. Take a close look at the region C. Yes. So if you do not use the co-line method, you may not recognize there are two vortex rings in front of these vortex rings, right? So you may just think, oh, we have one vortex ring, but actually later we have one and another weaker, right? The same thing, we reduce the isosurface, right? So you can see these additional, like the vortex co-lines are covered by the isosurface. So like you can find more vortex, know better about the real vortex structures. And then we look at the region D. I just said it before, so this figure I removed some weak small vortices. If I do not put any restrictions, what would the vortex co-line be like? So I go back so that you can have a comparison. So like here, it's we do not have this structure, but if I do not actually also delete some, but I just delete the 0.00001 if the vortex stress is less than 0.01, and we only delete very small vortex structure. You can see more vortex structure. So inside of these two main lambda vortices, actually they are still small, like small. So you can see small, and these vortex structures are all organized between the lambda vortices, right? Between the lambda vortices. And similarly, if we reduce the isosurface, these colines are all inside the isosurface, right? So you can see here the shape of the isosurface is similar to the Liouville's colines. So these colines should be correct, right? So we and these here also here like you see, you may question these colines are good or reasonable or not reasonable, but you look at the shape of the isosurface. Yeah, you can tell they are reasonable. So this method is powerful. It shows you a lot. It can show you a lot of detail, and we can use the colline method to study some mechanism. So one mechanism since it's a preliminary work, so we analyze the mechanism of the vortex ring formation. So like the traditional idea on a vortex filament to vortex ring is the Beer-Safra formula, right? The self-induction. So what these people do is, so first they think there is a vortex line here. Actually, the vortex they say means vorticity. I think it's 1986. The vortex they say means vorticity, and they apply this Beer-Safra formula, and they find these structures becomes okay. These structure become like a ring, and the ring become bigger, and the neck become narrow, and they think the ring pinch off, right? So we know the helping vortex will separate from the below lambda vortex and going up. So they think by this simulation, they think they found the mechanism. The mechanism is the Beer-Safra formula, right? Or they say self-induction. However, some limitation. So this simulation is not the NS equation. They just have these points, has the velocity at this point, and they simulate the evolution by using this formula, right? That's not the real governing equation. And the second issue is they use vorticity, right? Dr. yesterday said vorticity has so many problems on identifying vortex. And what will we say about the formation of the vortex ring? So we look at the region E. So we take a close at the region E, right? That's the region E will that position will going to form a vortex ring. So we take a close look at. So this is the region E. This is the top view, and this is the side view, and the number tells you the time series. So at time 1 it's like this, and at time 2 it's the stretch, right? The vortex structure stretch, and the gap become narrow. So first, it's not a connected line, right? They are separate, and second, it gets narrow. And then here, at the time 3, you will find the vortex ring, right? It's on top of this line. It's just appear, it's not from the deform of the connected vortex line. It just appear from the top. It's just here, and then so you may see this is the below. Okay, these two vortices are below, so not influence our conclusion. So here this one become longer, right? So these vortices become longer, and then you can see the at the beginning the line is some kind of like a straight line, but here there is a how to say fold here, right? Here is a fold here, and at the time of the it rise up, the fold become severe, and also we notice another initial stage of the vortex ring, and then we find two vortex ring near it, right? And also this ring also goes up, and the fold becomes more severe, and also it's become close, right? So the top view of this become close. It's become narrow. Okay, and then it's pinched off, right? So it's become narrow and pinched off here, and then next time step, the top ring connect with the bottom vortex line, so they connect, and then we continue doing this step. So it goes up, and we with the initial of the third vortex ring start to form. So also and the second ring connect to the bottom vortex structure, right? And then here, and these here pinch off at the next time, right? So the first ring, right, and it's separate with its original body, right? It's separate, and so here's like separate, right? A separate ring goes up, and then so another, and the third vortex ring forms, and this is the side view. So this ring is some kind higher than this ring. So that's our observation from the vortex cone lines, and so from the observation of the cone line, we can see the ring is not like what the self induction do. So it's a connected ring line, and then the head become big like a ring, and the neck become narrow and pinned off. So the ring just appear from the top, and to explain the reason, we draw the shear. The isosurface of this is shear. It's isosurface of partial U, partial W. W is the normal direction. So you can see there is a shear, right? So there is a strong shear layer at the region where, at the place where the initial stage of the vortex ring form. So it should be. So the real reason is the shear, right? Shear, and another observation is in one vortex there are two vortex cones, two vortex center. Like if you look at the isosurface, you may just say, oh, it's one vortex ring. But if you look at use the cone line, you find there are two vortex center. So, and we look at the slice at the region F. We look at the slice at the region F. So yeah, it's correct. We have two vortex center. So the real reason is Kelvin-Helmholtz instability, and you can see in the Kelvin-Helmholtz instability, you will form two vortex center, right? And the condition of Kelvin-Helmholtz instability is strong shear, right? Strong shear, and two vortex ring, right? And also one slightly top, one slightly lower, right? So their feature matched. So we think the real reason is Kelvin Helmholtz instability. And let's look at it's the moving. So we can see why I say this part is reasonable. So we look at this line. How does a span-wise vortices become lambda vortices? So it initially is span-wise. So you see, it becomes like curved, and then some small vortices appeared in front of it. Okay, and then okay. So I think we can use the code release session. We do not need that long time for code release. Yeah. I mean, I can start in the middle. So we look at here, right? So we observe these, and then these. Okay. They connected to the how to say, the W shaped like vortex structure, and after the connection, you can see they separate, right? They separate, and this part going up, right? So the middle, this part separate, and right, and sorry. Here, right? So so these parts separate from this, and it goes up. So this part is reasonable. They are not noise. Sorry, like if you see the full evolution process, you can tell they are not noise. They are just, they should be there, and we can continue seeing, right? So. Okay, and let's look at the video again. This time, I would like to bring your attention to here, right here. Here are the where we started the formation of helping vortex, so we can look at the movie and then observe how the vortex ring appear. So here, right? So you can see with the time going, it's become longer, right? So it become longer and narrow, and going. And then sorry. So here, so maybe not clear on the screen. So that's the initial, right? The initial vortex ring. So like the second ring, right? And the first ring, I think, separate and goes up, and a third ring. Okay. So I think that's that's the Lutex code line, and then we start to talk about the objective vortex identification method. So this figure shows you the streamlines in different frames. So in the first inertial frame, the streamline is like a straight line, right? So we cannot tell any rotation from the streamline. But if the observer is moving with the mean velocity, right? You can see there is a rotation in the by the streamline. Of course, streamline is not a good way to identify what is, but this example shows you the observers in different frames may get different vortex structures, or even there is vortex or there is no vortex. So we want to find objective vortex structures, even for the data collected by an observer that we do not know the observer's motion. So that's our purpose. So our purpose is giving us data. So it's the velocity field collected by an observer, and we do very limited information. We know very limited information about the observer. We don't know how the observer is moving, and we still want to find the objective vortex structure. And the idea is Lutex is Gaulin invariant, so that the Lutex structures will be the same in different inertial frames, right? So and then if we can find the vortex structure in one inertial frame from the data, then we solve the problem, right? So if we can find the Lutex structure, if we can use the data provided by the observer to give Lutex in any one inertial frame, we solve the problem. So and how to do that? So here I use the uppercase letter to denote the variable in an inertial frame, and use the lowercase two letters to denote variable in the observer's frame, and we assume the observer is a non-inertial observer, and suppose the observer is doing this moving. So this is the total velocity of the observer, and it's the absolute value. So it's the value. It's the velocity in the inertial frame, and the observer is doing translation and is doing rotating, right? Yes. And their velocity gradient has this relation. So the gradient in the inertial velocity gradient in the inertial frame is equal to this, and these are the observer's angular speed. And generally we have a transformation matrix T, but since we just need to find the result in any one frame, so we can pick a special frame to simplify the process. So we can let the frame we establish has the same origin and the same XYZ direction. So we do not need to do the coordinate transformation, and the T can become an identity matrix. So the relation is simplified to this, right? So we look at this relation. So the lowercase is the observers. That's what we can get from the observer's data, right? And this is the observer, and the left-hand side is the inertial data. That's what we want to get, right? And what is the gap? The gap is the observer's angular velocity measured in the inertial frame, right? So if we can determine this angular velocity from the observer's data, then we solve the problem. So that's the general idea, and how can we do that? So we first introduce a theorem. So we need to find the Vax, Vay, and the Vaz. So how to find them? So if there is a point, if we can find a point at which the vorticity is 0 in an inertial frame, and then we can know the observer's angular velocity is the negative 1/2 omega x. This is vorticity, and it's negative 1/2 omega y and negative 1/2 omega z. So if we can find this point, then the observers, okay, and these vorticities are measured in the observer's frame. So observer's frame. So if we can find such a point, and we know its location in the observer's data, and we just calculate the vorticity at that point, right? Then times negative 1/2, and the result is the observer's angular velocity in the inertial frame. Then we can find the velocity gradient in the inertial frame. So let me first prove this theorem. So we can decompose the velocity gradient into symmetric part and anti-symmetric part, and B is a zero matrix because we give the condition that zero vorticity, right? B is the vorticity matrix, so B should be 0. Then we bring the result to the relation between the velocity gradient in inertial frame and the velocity gradient in the observer's frame. So we get this expression, and we know B is 0. So we can know the velocity gradient in the observer's frame is the sum of A and these, right? And we know A is symmetric. Yeah, A is a symmetrical matrix. So this is a symmetrical matrix and an anti-symmetrical matrix, right? And the anti-symmetrical matrix is the vorticity matrix of these. So this matrix is the vorticity matrix of these velocity gradient tensor. So this term is negative or 1/2 omega z, right? So we got this relation. So yeah, so we prove this theorem. Okay, and the question is how to find such a point. Yeah, so the theorem is very beautiful, but the question is how to find the point, because we know nothing about the point information about the point in an inertial frame. All the information we get is from the observer, and how to find that. So we of course we need to use some extra information. So in this work because the strong vortices usually exist in concentrated regions, like that's the observation. So like the system tends to make it in an energy least state, right? The energy least means the fewer vorticity. So the vorticity usually concentrate in small regions. So we just if we accept this statement, then the zero vorticity point would account for the biggest percentage, right? So in a flow field, the zero vorticity point will account for the largest portion. So and if and this point at the same velocities, angular speed, and the new vorticity will also account for the largest portion, right? So the portion would be the same. So then we know the vorticity that accounts for the largest portion is the corresponds to the zero vorticity point in the inertial frame. So that's a way to find the reference point. So our method becomes, so if we get the velocity field from data of the observer, and we do not know the motion of the observer, so we first compute vorticity vectors in the observer's frame, and we just count which vector occurs most frequently, right? If we can find a dominant vector that vorticity that in that frame, then we know that vorticity corresponds to the zero vorticity in an inertial frame, and then we apply the theorem we talked before, and we can find the Vax, Vay, and Vaz, and use Vax, Vay, and Vaz. We can find the velocity gradient in the inertial frame, and from this like inertial velocity gradient, we can just calculate the Liouvtex. The Liouvtex calculated from this velocity gradient is the Liouvtex in the inertial frame, right? So we got the objective Liouvtex result. So this example still this. So this is the original. So what Liouvtex isosurface look like original, and then suppose we have an observer is rotating at this angular speed, and then you can see the vortex structures become distorted, right? This is not the real vortex structure, and from this data, we just find the portion of the vortices in the observer's data. So since the observer's angular velocity is uniform for all the domain, so if we can find the observer's angular velocity for a small domain, for a small region, then that result can be applied to the whole region, right? So to improve the efficiency, we just find the most frequent vorticity. So in this small domain, and you can see we do have a dominant vorticity vector, right? So the first, the most frequent vector accounts for around 40%, but the second frequent is only 1.10%. So by comparing the percentage, we can distinguish the points we need, and we apply the theorem, right? So this times 1/2 is the observer's angular speed. So this times 1/2 is 0.1028, the error is very small, 0.22969. And we know the observer's angular velocity is 0.1, 0.2, 0.3, right? So we get a very close estimate of the angular observer's angular speed. And also, so we also test this method in another subdomain, subsection, so also a small section. We can also find a dominant vortex, a vorticity vector, which accounts for more than 60%. And the second largest is only 0.83%. So there is a obvious leading. So this one is the vorticity we need, and we time -1/2. We also get the estimated observer's angular velocity 0.1, 0.23, 0.2020, 0.3014. Also very close to the real 0.1, 0.2, 0.3. And and we go back. So this is this is after we estimating the observer's angular speed, and we find the Lutex in the inertial, right? So we just apply our the just mentioned method, and you can find the result is almost the same as the original one, right? So our method has work, right? A summary. So vortex cone line shows the unique and both strong and weak vortex structures, and by analyzing the vortex cone line, we think the helping ring is from the common Helmholtz instability, and the cone line can help people study the turbulence mechanism, and we can achieve objective Lutex by finding the most frequent vortices. And thank you. Thank you.